Hello and welcome to this Python tutorial. So we just completed part 1, building the CNN. That is, we designed the architecture of our convolutional neural network, and now we're beginning part 2, in which we will fit our CNN to our images. So we will actually do it in one step, because we're going to use a shortcut, which is going to be very practical. It is the Keras documentation. And what will we use it for? Well, it's for a process called image augmentation that basically consists of pre-processing your images to prevent overfitting. Because what will happen then, we will get the results in this tutorial, but if we don't do this image augmentation, well, what we might get is a great accuracy result on the training set, but a much lower accuracy on the test set. So that is exactly overfitting. That corresponds to this particular situation where you get great results on your training set and poor results on your test set due to an overfit on the training set. So before fitting our CNN to our images, let's proceed to this image augmentation process. So right now we're going to take a browser because, as I just told you, we're going to use this Keras documentation shortcut. And so in your browser you can type Keras documentation. Alright, you can press enter, here it is. You just take the first link, Keras documentation, here we go, and that's the page we want. So basically on this page you get a lot of information about Keras and ready to use codes that you can take for your deep learning project. So right now what we need is some info or code for image augmentation, image preprocessing. So in these windows on the left, we're going to look for preprocessing. Here it is. That's the section we are interested in, and inside this section, as you can see, there is some info about sequence preprocessing, text preprocessing. Yes, indeed, deep learning can also be applied to text in a very powerful way, and of course, image preprocessing. And that's what we are interested in right now. So let's click on it and let's see what we get. All right, and the first thing interesting to see is this image data generator. That's the first function that we're going to use to generate this image augmentation. So what is image augmentation and how will it prevent overfitting? Well, we know that one of the situations that lead to overfitting is when we have few data to train our model. In that situation, our model finds some correlations in the few observations of the training set, but fails to generalize these correlations on some new observations. And when it comes to images, we actually need a lot of images to find and generalize some correlations. Because in computer vision, our machine learning model doesn't simply need to find some correlations between some independent variables and some dependent variables. It needs to find some patterns in the pixels, and to do this, it requires a lot of images. Right now, we are working with 10,000 images, 8,000 images on the training set. And that is actually not much to get some great performance results. We either need some more images or we can use a trick. And that is where data augmentation comes into play. That is the trick. Because what it will do is it will create many batches of our images, and in each batch it will apply some random transformations on a random selection of our images, like rotating them, flipping them, shifting them, or even shearing them, and eventually what we'll get during the training is many more diverse images inside these batches, and therefore a lot more material to train. And now we understand why it is called image augmentation. That's because the amount of our training images is augmented. Besides, because the transformations are random transformations, well, our model will never find the same picture across the batches. So all this image augmentation trick can only reduce overfitting. So in summary, image augmentation is a technique that allows us to enrich our dataset, our training set, without adding more images, and therefore that allows us to get good performance results with little or no overfitting, even with a small amount of images. So now, let's apply this image augmentation on our images. And to do this, we are going to use this shortcut I was telling you about, which is to take a ready-to-use code that we can find on this page and that corresponds very well to how we structured our dataset. Because as you can see, there are two ways to preprocess our images by applying image augmentation on them, it's either by using this code that is based on the flow method or this code that is based on the flow from directory method. And as you might have guessed, we are going to use this code section here because we are going to take our data from this data set that we built and that we structured this specific way so that our classes can be well identified in these separate folders, cats or dogs. And since this data set is in our working directory, well, that's why we use this function here, flow from directory. So inside this function here, instead of having directory, we'll put our data set. And so why did I call it a shortcut? Well, that's because with this code section here, we have everything we need to preprocess our images, augment them, and even fitting our convolutional neural network that we just built on our images. So basically, that's the end of the code, because this fit generator method will not only fit our CNN to the training set, but it will also test at the same time its performance on some new observations, which are going to be the observations of our test set. That is, the images of our test set folder. So that's perfect, we have everything we need. So this part is the image augmentation part, where we apply several transformations like the rescale. Well, the rescale is always compulsory and it corresponds to the feature scaling part of the data preprocessing phase that we know. And then we have other transformations like shear range, so that corresponds to shearing. You know, shearing is a geometrical affine transformation that is also called transvection, and where the pixels are moved to a fixed direction over a proportional distance from a line that is parallel to the direction they're moving to. So basically that is just a geometrical transformation for that same purpose of augmenting our images. And then we also have some other kinds of transformations like zoom range. So this is some sort of random zoom that we apply on our images. And we have also this horizontal flip that flips horizontally the images. And we also have a vertical flip, but that is not used here. We can have fun and apply all the image transformations that there are in this Keras documentation, but for now we will just use what we have in this example. That will be way enough, and you'll see that we'll get good results. Alright, so that is the image augmentation part. Now this image augmentation part is applied on the training set, and then we use again this image data generator function to this time only rescale the images of our test set. And then we have these two sections, train generator and validation generator. Well, these two sections actually create the training set and the test set. So what we'll do then when we are back to Spyder, well, we will call it training set and this test set so that we clearly see what's happening. And basically this is in this section that we will create this training set composed of all these augmented images extracted from our image data generator. And same, this section will create our test set that will be used to evaluate the model performance in this part of the code. And same, the images of the test set are extracted from our image data generator that was applied on our test set. And then we have this code section here that will fit our convolutional neural network model on the training set, as well as testing its performance on the test set. So let's do it. Let's take all this section here. We're going to make a few changes, but very few. And now let's go back to Spyder to paste this whole code section into our editor. Alright, and now we need to change a few things. The first thing that we need to do first is to import the class that will allow us to use this image data generator function. And this class is called image data generator. And we import this class from keras.preprocessing.image and import and eventually image data generator. Alright, so now we have our class. Now, next section. Alright, so in this section we won't change anything. We will rescale all our pixel values between 0 and 1, because you know, pixels take value between 0 and 255, and by rescaling them using this rescale equals 1 over 255, then all our pixel values will be between 0 and 1. Then shear range, that's to apply random transvections, and we will keep this 0.2 value. Zoom range, that's to apply some random zooms, and we will keep this 0.2 value. So these 0.2 values here are just some parameters of how much you want to apply these random transformations, and here we will take what Keras suggests. And then horizontal flip, that means that our images will be flipped horizontally, so that's fine, that will generate enough transformations so that we don't find the same image in the different batches. So basically we don't have anything to change here in this code section here, and we can move on to the next one. Test data gen, well, same, here we only need to rescale the pixels of the images of the test set so that they have values between 0 and 1, so that's all fine here as well, we don't need to change anything. But then we have this code section here that creates the training set, and here we have a few things to change. So first, let's give another name for train generator and call it training set. And let's press Alt Shift to align everything well. And so here, what do we need to change? Well, first, the first parameter is where we extract the images from which directory. So it's not from the data/train directory. Let's see where it is from. Well, remember we have here our dataset that is composed of two subfolders, the training set and the test set. And so since here the section corresponds to the creation of the training set, well, we need to specify what this training set is, and therefore we need to specify the path, that is dataset/training set. And we don't have to specify the whole path that leads to this dataset because this dataset is already in the working directory folder. Perfect. Then target size. So target size is the size of your images that is expected in your CNN model. So as you can see here, we chose a 64 by 64 dimensions for our images, and therefore here we cannot keep this 150 and 150. We need to put the dimensions expected by our CNN, that is 64 and 64. Great. Then the batch size. So that is the size of the batches in which some random samples of our images will be included, and that contains the number of images that will go through the CNN, after which the weights will be updated. So we will keep 32 here. This actually looks fine to train our CNN. And finally, class mode. Well, that's the parameter indicating if your class, your dependent variable, is binary or has more than two categories. And therefore, since we have two classes here, cats and dogs, well, the class mode is binary. So great, this section is now ready. Now let's move on to the next section, validation generator. So let's actually call it test set, because this code section will create the test set. And now let's align everything. So I'm going to press Alt Shift. And now let's see what we need to change. So first, we need to input here the path that leads to the test set. And that's exactly the same as for the training set. We need to input here data set first, and then test set instead of validation. Test set. Here we go. Then target size. Well, that's the same. The images of our test set will be expected to have the 64 by 64 dimensions by our CNN, and therefore here we also need to replace 150 by 64, and same here, 64. All right, then we will also keep this batch size of 32 and same class mode binary because we have our binary outcome. Great, and now finally last code section, the model fit generator, where we fit our CNN to the training set while also testing its performance on the test set. And therefore, well, first let's align everything again. Here we go, and now let's change the last things. Well, the first argument that we need to input here is our training set. So we will replace train generator by training set. Then the second argument is the samples per epoch. Well, that's simply the number of images we have in our training set, because remember, all the observations of the training set pass through the convolutional neural network during each epoch, and since we have 8,000 images in our training set, Well, here we need to replace 2000 by 8000. All right. Then number of epoch. Well, that's the number of epochs we want to choose to train our CNN. And here 50 might be a little too much, so we will take 25 so that we don't have to wait for too long to get our results. Then validation data. So that corresponds to the test set on which we want to evaluate the performance of our CNN. And that is of course the test set. So we will replace validation generator by test set. Almost good. The last parameter is NBVAL samples, and that corresponds to the number of images in our test set, and that is 2000. Perfect! And now we just need to change one last thing. Can you guess what it is? Well, we are using this fit generator method to fit our CNN to our training set and test its performance on the test set at the same time. And this fit generator method is applied onto our CNN model. But our CNN model is not called model, it is called classifier. So we just need to replace model here by classifier. And let's align this again, Alt Shift, so that now we apply this fit generator method onto our classifier to fit it to the training set and test it on the test set. So great, now everything is ready. We are ready to execute each of these last sections one by one, and eventually we will get to our final results. So let's execute them one by one. We're going to start by importing the image data generator class. Here we go, well imported. And now let's proceed to this next section to, actually prepare the image augmentation with this train data gen, which is an object of the image data generator class. So in this section, we are creating this object. So I'm going to press Command plus Enter to execute. And now our object of the image data generator class is created. And this object is the object that we're going to use to augment the images of the training set. And now we're going to do the same for our test set. We are going to create another object of the image data generator class. And this object will be used to pre-process the images of the test set. And then next code section. In this code section, we apply the image augmentation itself on the images of our training set by at the same time resizing all our images of the training set into this 64 times 64 dimensions, and by creating some batches of 32 images. And then our CNN will be trained on these images in all the different batches. Okay, so let's execute this section. And as you can see, that's actually very interesting to see. Well, Keras found 8,000 images belonging to two classes. And that is specifically thanks to the way we organized our images into our dataset folder. You know, splitting this dataset folder into a test set folder composed of 2,000 test images and the training set folder composed of 8,000 training images. So that's why I was telling you, this is a great and simple way to pre-process our dataset when we work with images. And then next section is the same, but for the test set. In this section, we are creating the test set and we are resizing all the images of the test set into the 64 by 64 dimensions, and at the same time creating some batches of 32 images. So now let's execute this section and we can guess what we're gonna get now. We should have found 2,000 images belonging to two classes. Let's check it out. I'm going to execute, and here we go. Found 2,000 images belonging to two classes. So of course, that's the 2,000 images of our test set. And now, finally, last section. But I have to warn you, now this is going to take some time. So a good idea right now would be to run this code just before you have some lunch or dinner or even take a nap. I'm going to take a nap right now, but what I mean is that it's not going to take 10 seconds to execute. It'll be rather 10 or 20 minutes. But anyway, now we are ready to execute and find out about the final results. So let's check it out. I'm going to execute right now. Are you ready? And go! Here we go. First epoch, 1 of 25. So as you can see, it's going to take a while because right now it's training on the 8,000 images of the training set, and it will do this over 25 epochs. So let's take a break, let's get a coffee, and let's this run on its own. I'm gonna take a quick nap, and I'll see you in a couple of minutes. And here we go. The training is over. We obtained an accuracy of 84% for the training set and 75% for the test set. So what do you think of these results? Well, not too bad, but not too good either. Okay, so first we obtained this 84.5% accuracy on the training set. That is not bad, but that is not what we are mostly interested in. What we are mostly interested in is the accuracy of the test set, which is equal to 75%, and the difference between the accuracy of the training set and the accuracy of the test set to assess whether there is overfitting or not. So 75% accuracy on the test set is not bad. That means that we get 3 correct predictions out of 4. So that's actually not too bad. But then we get quite a large difference between the accuracy on the training set and the accuracy on the test set. So it's not like there is important overfitting, but still there is a lot of room for improvement. Not only we can improve the accuracy of the test set, and a good goal that we can set ourselves would be to make this accuracy reach an accuracy over 80%, and besides what we would like to get is a smaller difference between the accuracy of the training set and the one of the test set. So that's our challenge. Let's try to increase this accuracy of the test set over 80% and decrease this difference between the training set accuracy and the test set accuracy. This is what we'll do in the next tutorial, but before you get to this next tutorial, try to figure out some ideas to improve that and reach these goals. And I'll give you a hint, the answer to this improvement is in the title of this part. So good luck, and I'll see you in the next tutorial.